So hi everyone, can you see my screen in presentation mode?
Yeah.
Fantastic. Thanks Zinta. My name is Iulia Marginean. I'm a PhD student at the University of Oslo and the Center for International Climate Research in Norway. The paper that I'm going to talk about today is, or this work is part of a larger project called MCLIC that focuses on transdisciplinary research on urban overheating. And also part of this research was conducted under the Young Scientist Summer Program at YASA in 2021. And it's related to the demography and heat stress and what is the role of population dynamics and demography in climate risk projections. So a little bit of the context. In my PhD, I look at the climate impacts on human health and more specifically how heat stress affects health in urban environments, and also how what we can learn and how we can project future risk better. So I take a transdisciplinary approach where I try to combine climate science with epidemiology and demography. And for this, we use an extended version of the IPCC risk framing that doesn't only include the interrelationship between hazard exposure and vulnerability, but also considers risks coming from response to heat stress and heat risk. But in this particular paper, I would like to focus on the vulnerability component of the risk framing. And perhaps this is a very good example of how epidemiology and demography can come together in a transdisciplinary manner. So from epidemiology literature, we know that, or we've learned that certain population groups are more susceptible to heat than others. So for example, older adults above the age of 65, infants whose thermoregulatory system is not yet fully developed, are more vulnerable. Some studies find that women are more susceptible to heat than men, but the results vary from location to location and from method to method. So this is still inconclusive at the moment. We also know that the socioeconomic status plays a role in quantifying or modeling the vulnerability to heat stress. But because in this study, we want to use demographic variables, and we also know about that there's a link between educational attainment and the socioeconomic status, we use education as a proxy in this study. So we see that we can quantify vulnerability with using demographic variables, and also we want to do population projections of population dynamics under alternative scenarios. So there's the problem with this approach is that even though all the demographic variables that I've outlined in the previous slide are contained in the Shared Socioeconomic Pathways database, this data is fairly coarse. So as we can see here for the case study of Madrid, as an example, most of this data is at the city level or at the country level or at the gridded level. And for Madrid, in this case on the map, we can see that we have about 20 to 25 data points, which is not enough to really see the changes and mapping out the vulnerable clusters within the city. So in this paper, we are trying to, we aim to downscale the SSP projections and develop higher resolution population projections. So what we are essentially looking to find out is where do vulnerable people live within the city, and how do they move around over time. And to do this, we use a method called Bayesian model averaging that I want to introduce briefly here. This is a bit of a busy slide, but I will take it step by step and also argue for why we use this method compared to a more classic frequentist approach. So BMA is essentially a regression analysis type of model. where there's a dependent variable, if we assume a linear model structure, and a set of independent variables that are contained in a matrix X. And one of the benefits of using a Bayesian approach, and specifically this Bayesian model averaging, is that this X matrix can contain a very large number of variables. So in this preliminary study, we use 87 variables to determine the dependent variable Y. Also, another Bayesian feature or feature in the Bayesian analysis is that, as a Bayesian would put it, we let the data speak, meaning that all these variables, independent variables and combinations of these variables, receive certain coefficients or weights. So if we, in the matrix X, if we assume a K number of independent variables, 87 in this case, the model will combine or calculate all the possible combinations between these variables, resulting in a 2 to the power of 87 number of models. And another feature of Bayesian approaches is this prior, which refers to prior knowledge or beliefs of the researcher conducting the analysis. And I will explain a bit later how we use this prior knowledge. And with this formula, we solve for posterior probabilities. And what this means, we can see here in the graph on the right-hand side on the top. So starting with the prior, in the case of an uninformative prior, we can see a very normal distribution, but after the model is run, some of the variables and combinations of variables receive a higher or a stronger weight. So in this case, we have a combination of 23 different variables that are the best to explain the dependable variable Y, which could be, for example, highly educated women above the age of 65. Okay, so moving on to the how we project this and how we conduct the future analysis. For education, for example, we have data for from the city of Madrid for 2010 and 2020, raw data at the census tract level. As input to the model, we use mortality and fertility data, migration, education that is disaggregated for age, different age categories and between the two sexes, so male and female. We also use a district dummy, but I don't really have so much time to get into the details on that. So we tap all this information into the model, and we obtain projections for the same demographic structure for 2020. So if we tap in data from 2010, the output is for projections for 2020. And to verify how well the model performs, we compare this data with observations, so raw data from 2020. And in the preliminary analysis, we find that the model performs fairly well. So the projections are very well aligned with the raw data. So we use this, the same framing. So for 2030, for example, we use the projected data or model output from 2020 to tap into the input for 2030 and so on in 10-year steps until the middle of the century. And the projections that are based on the raw data or the observations data from the city of Madrid, we consider to be in line with the SSP2 or the middle of the road scenario. And for the other shared socioeconomic pathways, we use this prior knowledge in order to give more weight to the narratives in these scenarios. So a glimpse of what this looks like. In the end, we can we use this method to do a spatial mapping of vulnerable clusters within the city and really capture the heterogeneity by demographic variables. And here's an example of a projected change in highly educated female population between 2010 and 2030. Highly educated female population means higher educational attainment, bachelor's, master's, and doctoral degrees. And we can already see, even though it's 20 years difference only, we can already see some patterns throughout the city. So in the city center and in the western and some of the northern census tract polygons, we can see that there's a higher projected increase in higher education in women. And there's this belt on the southern part of the city or the city center that sees a much lower increase in female education, with even negative values in some areas of the city. And so this type of modeling helps decision making to design preparedness and response strategies that are targeted at the most vulnerable groups and most vulnerable areas in the city. And so to conclude, there are multiple drivers of vulnerability, and some of them are we are able to quantify using demographic variables. However, there are other, this is perhaps one of the limitations of this study, and recommendations for future research is how to integrate other spatial features such as proximity to green and blue spaces in this framework. We can also see that this research framework is useful for decision making, to design effective prevention strategies and response to heat stress that are targeted at vulnerable groups. And this is easily transferable in other locations and other cities, but the spatial resolution and the degree of detail that we can obtain is highly dependent on the input data. There's also, this framework is focused on one single hazard, which is heat stress in one sector. So it does not account for interacting hazards and compound risks. Thank you very much. I think I'm on time. So if there are any questions.